Hi everyone, today we're going to continue on image and null space. Today's video could probably be the last video. I'm going to try to finish it up in this video. Even though we might spend more than 2 days on this sections, but if I finish this in this video, then that will mean that you get a break from watching the video and just simply have to process them and have extra days to ask questions. So if I remember correctly, the last thing we talked about was the definition of what is a null space and talk about how to find it. And you realize that the null space is very likely to be a subspace of the domain, as a matter of fact it is. So I'm going to go ahead and state the theorem that give you that facts. Even though I've been saying that, but I haven't really give you the theorem that's stated it. So here's what it says. So let's say we have a function f that maps from v to w. And let's say it is a linear function. Let n be the set of vector v in the vector space v such that f of vector v is equal to 0 vector. What we know is n is called the null space of f, and it is a subspace of v. The idea is that because of the fact that f is linear, therefore it forces 0 to always be a solution to this equation, and therefore satisfy the subspace requirement. Okay, and the interesting thing about it is that any two element in the null space would have to be, and the sum and scalar multiple have to be in the null space. So I'll show you how that works. So give you a very simple proof of this theorem. So remember, in order to show that n is a subspace of v, I have to show three things. Number one is that it has to have the 0 elements, it has to have a addition closure and a scalar closure. So let's go and go for these first things first. Let's talk about the 0 vector. Okay, which we can pretty sure that f of the 0 vector would definitely equal to 0 vector in the term of linear function. The reason why you can think of it as like what we choose to do is to do f of 0 times any vector x would become 0 vector, and that would equal to 0 times f of whatever vector x is, and therefore would have to be 0. Now closure is probably what's interesting to show, so I can go and show this. Okay, but okay, maybe we'll write this out too. So why is this true? Because let's say you have f of 0 times some vector x, then that will always equal to 0 times f of vector x, and 0 times vector x would definitely be the 0 vector, and 0 times the 0 number times some f of vector x will also be the 0 vector. So therefore indicate that f of 0 vector must equal to 0 vector. So therefore showing that the 0 vector must be in n. Okay, so now let's do the closure thing. So let's do the vector addition closure. So let's call the addition closure. So let's say we have u and v in the null space n. So what does that imply? That implies that f of vector u must equal to 0 vector, and f of vector v must also equal to 0 vector, because that's the criteria of being in the null space, is that when you plug into the function f, you get the 0 vector. So now let's show that f of u plus v is also u plus v is also in the null space. So I'm going to do is I'm going to try to find f of u plus v and try to find out what it is. So because f is linear, if I do f of u plus v, that will mean the same thing as f of vector u plus f of vector v. That's because the function f is linear. And since we already know that f of vector u is 0 and f of vector v is 0, then therefore the sum of 0 vector plus 0 vectors must be 0, and therefore indicate that vector u plus v must also be in N. And so we can probably already figure out how to write out the proof for scalar multiplication closure, because it's basically the same concept. So let's say vector u is in N, and therefore imply that f of vector u is equal to 0 vector. So now what I want to do is, what if I do f of r times vector u? What will happen? So because f is linear, r times f of r times vector u is the same as r times f of vector u. And since we already know that r times r of vector u is 0 vector, that just becomes r times 0 vector, which basically just becomes 0 vector. So therefore tell me that r times vector u must also be in N, and therefore show that it is closed. So since the null space satisfies these three conditions, it has a 0 vector in N. If u and v are in N, u plus v also in N. And if u is in N, then r times u is also in N. Therefore, would tell me that this must be a subspace. So that kind of proves theorem 3.4.2. Now, yesterday's video already talked about this one, so I'm going to go and state this theorem, and I don't think we need to prove this one. Theorem 3.4.3, which is basically a restatement of a theorem that you already know, which is theorem 3.3.3. So if you want to go back to your notes and look up what theorem 3.3.3 state, you could, but I'm going to state theorem 3.4.3. It's a linear function is 1 to 1 if and only if this is true, if and only if its null space is basically the trivial subspace or the 0 subspace that consists of only one element, which is the 0 vector. Oops, of only there you go, of only the 0 vector, and that will make the linear function 1 to 1. All right, now show you some example. Okay, so let's try to figure this one out. Okay, a very simple example to so that we can use this theorem. Consider the integration operator. So you can think of this integration operator as kind of the inverse of the differential operator, even though that's not true. The reason why it's not true, because differential operator is not 1 to 1. We already established that the differential operator is null space is equal to any constant function. So therefore, the differential operator is not 1 to 1. So therefore, you cannot think of the integration operator as the inverse of it, even though it's almost like the inverse. Okay, let's consider the integration operator defined on let's say continuous function, and I'm going to just say for negative infinity, positive infinity. It could be any domain that we want. With this being the integration operator. So I really don't have a fancy word for it, but as a matter of fact, we won't be using integration operator that much. We'll most likely be using differential operator because we are talking about differential equation. So I'm going to just call it this: f of u of x is equal to integral from 0 to x u of t dt, which equal to some function v of x. Notice a change of variable involved because when you integrate the function u, I want the upper limit to be x so that I can define a function in x. So therefore I change the variable inside to be t. You know what? How about we, it does kind of confusing because it does look like this is like composition of function instead. So how about we do the following? Oops. How about I'm going to call the integration operator capital I. So that way, we usually use a capital letter to indicate operator. Okay. I'm going to go and tell you this is true. The integration operator is linear. It's a linear operator. So we're not going to prove it, but if you want to, you can definitely pause the video and take a minute to go through the proof. It's not difficult to do, okay, because it all rests on the fact that when you add two functions together, integrate is the same thing as integrating and then add, because we proved that in BC calculus. And if you have a constant multiple inside the integral, that can be pulled out. So it's basically the same exact concept like the derivative. So it's not hard to write out. If you want to do that, you can. So the question that I want you to do is use theorems 3.4.3 to show that f is 1-to-1. So I'm going to go and tell you that it is 1-to-1. I just want you to show that it is. So take a minute to try to figure it out. Feel free to pause the video and then unpause the video once you're done to see how that works. So I'm just going to continue, and it should be pretty easy to argue the fact that it is 1-to-1. So how do I show that this is 1-to-1? Using theorem 3.4.3. So what I need to show is that there's only one element that I can plug into this integration operator that will allow me to get 0 as the output. Okay, so in this case, what I need to do, I have to solve this equation. And once again, here often students get confused. I'm not talking about the real number 0, but rather talk about the 0 function, which basically means z of x equal to 0. Okay. So how does that work? Well, let's find out. So if I apply the integrating operator to the function u, that means that I have to find out integral from 0 to x u of t dt would equal to the 0 function, which is 0. So how does that work? So, well, there's basically two primary ways for you to have a definite integral and result in a 0 value of a definite integral. Okay. Well, okay, maybe 3 ways. So number 1, the first and most straightforward way is if you go from the same number, the lower limit and the upper limit, and that would force the entire integral to be 0 regardless what the function inside is. But in this case, that's not allowed because I need the top limit to be a variable x, meaning the top limit can be any numbers that I choose, and it will create some kind of function. So meaning I need to somehow, no matter what this number is, I get 0 as an output when I form this integral. So this number cannot be a fixed number as like 0 to 0. So therefore that option is out. 2, a definite integral is what we call the net sign area. So therefore it's possible that when you integrate from 0 to x, you get 0 as an output because the net sign area is 0. But the problem is the same as before. That would mean that there might be some specific value of x that will make that happen. But it won't make every value of x the area is 0. Okay, like if you do like the sine curve or cosine curve, then some value, a fixed value of x would always give you a 0 value as the net sign area. But it won't be for every value. In here, what we need is a function u of t that no matter what I put for x, I get 0 as an outcome. And that only allows one possibility. is when you integrate 0. When you integrate 0, what you have is basically the horizontal line that is the x-axis. So no matter where you choose x-axis, the area between the x-axis to the x-axis is always 0. So therefore indicate that the only solution to this equation is just the 0 function. Oh, sorry. Oh. It should be u of x. It must be equal to the 0 function, which is just 0. So therefore, tell me that the null space, in this case, the null space of I is just the 0 subspace. There's no other function that I can integrate from 0 to x and guarantee to always get 0 no matter what x is. 0 function is the only one that would do that. Alright? So that's null spaces. Now the question then would be, why are we interested in something like that? Well, I mean, obvious reason. Number one is that it helps us identify whether the function is one-to-one or not. But more importantly is the following. Okay, what we're going to talk about is something called non-homogeneous equations. And some of you probably remember learning that last year in multivariable calculus anyway. And some of you might also remember some of the theorem that kind of relating to this talk about the homogeneous solution, which if you think about it, the homogeneous solution is kind of what the null space is, technically speaking. So the null space of a linear function f of vector x is actually an important part of how we can solve, how we can represent the solution set of a equation f of vector x equal to some fixed vector b, where b is a fixed vector in the image of f. So therefore b must be an output that the function f can actually have. And in this case, b, obviously we're talking about b not being the 0 vector, because if b does equal to the 0 vector, we are basically talking about the null space of the function. So here, if b is non-zero, then we actually talk about some kind of solution set that's not the null space. But the problem is that the null space still becomes a very important and integral part of what the solution set would be. So terminology, which you already know from multivariable calculus. So let's say if you have the equation f of vector x equal to vector b, if vector b is not the 0 vector, then this equation is called a non-homogeneous equation. Okay, and the equation f of vector x equal to 0 vector is often referred to as the associated homogeneous equation. So this equation is somehow tied into the non-homogeneous equation. It's called the associated homogeneous equation. And of course, eventually we will talk about differential equation the same way as we refer to here. And the idea is that we call, or also notice the following. Notice that the solution set to the associated homogeneous equation is basically called the null space of F. And that's the connection right here, is why we talk about homogeneous equation. Talk about null space because it ties into the associated homogeneous equation. Now, what's important about the associated homogeneous equation or the null space? Well, it's summarized in this theorem. So this theorem is actually a kind of restatement to a theorem that you learned back in last year multivariable calculus chapter 2. The only difference is that when you first learned about it in last year in multivariable calculus in chapter 2, the theorem more so just applied to the Rn vector space. But now we can actually talk about any vector space that we want, because we established that some of the other vector spaces are actually behaving similar to the Rn vector space. So therefore now we can use what we know about them to actually extend to other vector spaces too. So this is more a generalization of theorem. So let's say let F map from V to W be linear. Okay, we have to have a linear function to begin with. Okay, let's say we have a vector. Let vector x sub 0 be a solution to the equation f of vector x equal to b. So meaning imply that when you plug in x sub 0, f of vector x sub 0 would equal to vector b. Now, let's say let V be a solution to the associated homogeneous equation f of vector x equal to 0 vector. So basically implies that f of vector v is equal to 0 vector. Then what we know is the following. Then the set of all solution to the equation f of vector x equal to vector b will consist of all vectors in the form of vector x sub 0 plus vector v, with vector v ranges from all the solutions for the associated homogeneous system. So therefore, someone might remember the theorem that we learned in chapter 2 of last year, which say that when you have a linear system of equation and it has infinite solution, or well, actually it doesn't have to have the infinite solution, but if it does not, then it's not as exciting. If you have a system of linear equation, then the solution is always formed by adding the homogeneous solution to a particular solution. And that is basically what this theorem is saying. Except that in this theorem, the vector x sub 0 and vector v doesn't have to be like vector in Rn, but it could actually be any thing, depending on what the vector space v and w is. Okay? Now, I'll show you some example to illustrate. But the idea is that we will be using like a specific example, a solution, as well as a homogeneous solution to kind of put together to form a solution set. So the first example would be something similar to what you remember seeing last year. And then my second example will kind of illustrate how we go use this in what we're doing in differential equation. So here's my first example. Let's consider the linear function f that map from R3 to R2, such that this is true, such that f of vector x is equal to 1, 1, 1, 0, 1, 2 multiplied by x, y, z. If f of vector x is equal to 3, 3, 3, 3, apply. So there are different multiple ways to solve this. You can just simply try to solve this like you would do any system equation. But I want you to apply theorem 3.4.4 to find the solution. And on your next test, the question will be specified that you have to use the theorem to solve it, because I want to see you understand the concept of putting a particular solution to the system of equation, or to the linear function equation, and also finding the null space and combine them together to form the solution that you want. So how do we actually use theorem 3.4.4 to actually come up with the solution? So, well, two ways. Number one is you will first solve for the homogeneous solution, or the null space of the solution first. And once you can do that, then you would then try to figure out, is that a way to find a very specific solution to this equation. So let's go and do the first thing first. So let's start with the null space. Or if you want to, you can think of it as the homogeneous solution. They are kind of the same thing. So that would mean that I have to solve this equation. So meaning f of x, y, z is equal to 1, 1, 1, 0, 1, 2 times x, y, z, and that's equal to the 0 vector. So, I mean, that just basically forms a system of equation, x plus y plus z equal to 0, and then y plus 2z equal to 0. So how do we go about solving this? Well, plenty of different ways to do it. I guess we can just try to reduce the system. Notice that, see, a lot of things that you probably remember learning last year become important here. You look at this system right here. This system has 3 variables, but only 2 equations. Therefore, this system guaranteed to have infinite solution. Okay, so it will be 1, 1, 1, 0, 1, 2 with 0, 0. So, it might take you a few minutes to solve this system, but it actually only requires one step to put this system into most reduced form, and that would be just to subtract row 2 by row 1. So negative row 2 plus row 1 will basically give you 1, 0, negative 1, 0. 0, 1, 2, 0. And that's in the most reduced form because you now have 2 leading entries right here and right here. And then all the other element in the same column that has a leading entry is now just 0. So therefore indicate that what I have is x minus z, x minus z is equal to 0, and y plus 2z equal to 0. So therefore the top equation tell me x equal to z, and the bottom equation tell me y equal to negative 2z. And so if I simply just let z equal to our new parameter t, I can then say the solution that we're looking for, x, y, z, would just simply equal to t multiplied by 1, negative 2, 1. That means our null space is actually spanned by one single vector, which is 1, negative 2, 1. And some of you who probably remember learning from last year, since this null space have only one direction vector, it is a line. We actually talk about a line that goes through the origin in R3. And in R3, because our domain is R3, and so therefore this is a line in R3 because this has to be a subspace in R3. So now the second part of the problem is to simply try to find one solution, any solution that you can come up with. So the second part is to find a particular solution, any one solution to the equation f of vector x is equal to 3, 3. So that's actually not that difficult to do. And as a matter of fact, most students, when I ask for this, they come up with at least 2 possible choices. Okay? So I'm going to give you a few minutes to just to think about it. So pause the video to think, and then unpause the video. And when you think of at least one of them. So the 2 most popular choices for vector x sub 0, which is a particular solution, would be this one. The first one is just 1, 1, 1. If you think about it, 1 plus 1 plus 1 would equal to 3, and then 0 plus 1 plus 2 would also equal to 3. So therefore, if you just plug in 1 for x, y, and z, you basically will have that. Another very likely choice would be this one, 0, 3, 0. Because the idea is that in this case, when you multiply 0, plug in 0 for x and 0 for y, you basically just have 1 y on top and 1 y for the bottom equation, 1 y for the top equation. So y of both 3, y of 3, that will basically give you the output 3, 3. Okay, so therefore, what is the actual solution to this differential equation? Well, there are 2. Well, more, but based on that, depend on which one of these 2 you find. If you find the first one, you can say that your solution in this case is vector x equal to t times 1, negative 2, 1 plus 1, 1, 1. If you recognize the bottom one, you can say that your solution is t times 1, negative 2, 1 plus 0, 3, 0. Or if you find some other vector x sub 0, then it could be whatever you choose. All right. So this, as I say, is very similar to what you remember learning back in chapter 2 last year. So how about let's talk about something more relating to what we are doing right now. So it's another example. Imagine the following. Let's say, let's suppose we want to solve this differential equation. So it really doesn't matter what it is. I'm just trying to show you generally what's happening. So let's say this differential equation takes some kind of function y of x and give you some kind of specific output g of x. In this case, I'm going to say where d is called the differential operator. And let's say g is some kind of continuous function. Oops. in some kind of domain from A to B. So now the question is, can I show that the solution of this differential equation will satisfy what the theorems 3.4.4 say. So basically meaning that if I find the solution to this differential equation, I want to show that this solution is made of two parts. One part is the homogeneous solution, the other part is a particular solution that satisfies the equation. So satisfy theorems 3.4.4. So how does it work? So, well, let's take a minute to think. Remember, if I want to apply theorem 3.4.4 to solve a linear function equation, what I need to do is simply note that I need to find this homogeneous solution and a particular solution, and then see how they work. So suppose here's what happens. So first thing I want to talk about would be the homogeneous solution, or the null space. And you actually already know, if we take the derivative of the function y of x, and let's say I get the 0 function, then therefore indicate that the solution y, I'm going to go and put down y sub h of x, must equal to some constant c. And x here indicate the homogeneous solution. Remember, that's the null space of the differential operator. 2. Let's say we're looking for any one solutions, any one, or sometimes referred to as a particular solution, any one solution to the equation d of y of x is equal to lowercase g of x. So in this case, what I'm going to do is I'm going to just let capital G of x be an antiderivative of g. Basically meaning that if I take capital G of x and I take the derivative of that, I get lowercase g. And in this case, therefore, now I have my answer. Therefore, the solution to this differential equation, it basically just equal to y of x equal to the particular solution, which is in this case capital G of x, plus the homogeneous solution, which is the c. Notice that is where the plus c came from. See, in BC calculus, you learned that the plus c is more like a vertical translation, because when you differentiate, the constant plus c would go away into 0, because any derivative of a constant go to 0. But now, from linear algebra perspective, you realize that that is basically the homogeneous solution of the null space. And also important part, which is very important, and that's probably the last thing I want to talk about, because the video is getting too long already, is that this plus c creates something very important about our differential equation solution. Is that because of this plus c, the homogeneous solution of the differential equation, that create the scenario where whenever we solve a differential equation, our solution is almost always an infinite solution set. Meaning that infinite number of solutions that will satisfy a differential equation. And you also already learned that if you have some kind of specific information, quote unquote, initial values, then you allow you to actually find a specific solution from what we refer to as general solution. So those are terminology that you probably remember learning in BC calculus, and we'll talk more about it later on, so don't worry about it. At this point, I'm going to have to stop the video, but that is the end of 3.4, so I'm glad that I squeezed everything into this one video, so that way you don't have to watch another video for third day and have more time just to digest and ask questions. Alright, I talk to you guys later. Bye bye.